Good morning, everyone. What a pleasure to be here. Yeah, it is cavernous once you get way back there. This is such a treat. And yes, it's a presentation, but there are so many people in this room that have got a chance to come down and see the Sac Valley that have been a major part in Rachel, in Carson, in Jacob Montgomery, of everything that's going on. So please interrupt me if you have questions. It is so much nicer to have a conversation than just to get a download. And there's plenty to download, don't get me wrong, and I can talk a lot. But please, throw your hand up or just shout out a question at any point, should you have one. What I want to tell you, talk to you, share about is the journey we've been on, not just in the last decade and a half, but really in the history of both change and understanding over the last 150 years in California, since European American colonization of that Great Valley that we're focusing on today, but really the whole state and the West Coast. And the reason that we're here today is, yes, I'm going to be talking about the Sac Valley. Yes, we're going to be talking about rice. Yes, Massa's field is 4 acres here, but really it's not a story about rice. Really, it's not even a story about fish, although fish are the wonderful window into what a river is and how not just fish, but all of the native biota, all of the life is so intertwined and dependent on that river. That river that isn't a thin blue line, but is the summation of all the different interaction between water and the landscape through which that water flows. The sequences, the patterns that life reacts to, responds to, and is shaped by, that create this wonderful regional specificity, the idea of home. What I really want to talk to you about is home, and what speaks to home more powerfully than salmon, right? And in that way, here we got a clicker. All right, so California, and in the middle of California is this tremendous valley, ringed by mountain ranges, right? I mean, this is one of the most productive valleys on earth. The northern lobe is the Sacramento Valley, the southern is the San Joaquin, watered by the high Sierra Nevada snowpack to the south. We have an amazing volcanic system. It's the southern part of the Cascades. The chief Sisk and her family live on the flanks of Shasta, this incredible mountain that's part of a volcanic landscape where when water falls on that landscape, it filters into those porous soils and comes out as consistent cold water springs. We have a coast range that isn't as tall as the Sierras, but still provides a myriad of rain-fed rivers. All of this is just to say that while we're focusing on the Sacramento, what we're really talking about is patterns. And the Sacramento Valley has very distinct patterns of water and landscape that have led to it being the most diverse Chinook salmon watershed on earth. We have more different kinds, more different runs, more different timings of salmon using this landscape than any other place because there is such a diversity of landscape, of timing of snow and rain, and the sequences of biophysical condition to which these critters could adapt, right? And so in the Sac Valley, we have headwater springs. I was just talking about Mount Shasta, Mount Lassen, the volcanics. That's all the way up here, the headwaters of the Sacramento. And that specific set of patterns led to a Chinook salmon that enters the Sacramento River from the ocean, all the way down here at the Golden Gate, right? The Golden Gate is a gap in the Coast Range that the Sacramento, San Joaquin rivers flow out. It's not a bridge, right? This is the landscape that these critters know and understand. So the winter run would come through the Golden Gate and take a left up into the Sacramento Valley in midwinter when our Mediterranean environment, where it's a drought every summer, but every winter we can have, pretty substantial rainstorms, snow melt. So it's the most consistent time for a fish to enter and travel the 300 miles up the Sacramento Valley to a consistent cold water source. Those winter run are accompanied by a spring run. The spring run are found in the snow-fed mountains of the Sierra, coming down on the east side of the valley. And the spring run, as you guys well know, basically surf the snowmelt that comes down later in the winter and early spring. And then we have a fall run that is really a rain-adapted fish. In California, it doesn't really start to rain until what we call fall, but fall often starts in December nowadays. And so you have a run of fish that is coming in and employing the lower elevation habitats of the valley floor, coming in later in the season, swimming up to where those streams start to climb into the foothills, where the gravel is deposited, putting those eggs into the gravel there. It's warmer down there. Those fish are those eggs are going to hatch earlier. Those fish will need to get out of the valley because it's like the furnaces of hell there in the summer. It's 110 degrees, right? These are cold water fish. So that fish, not having cold water year round, the fall run are going to need to get out of the valley relatively quickly. All of that is just to say, not to drill in the details, but to get our mind into this way of understanding pattern, of understanding our job. And our job is to allow not just salmon, but all of our native plants and animals to recognize the place that they are from. And how do you do that? You present them with not an exact replica of the landscape and the patterns to which they're adapted and under which they evolved, because there's been really fundamental alteration. And more than anything else, it's full of people now, this valley. It's one of the most lucrative and most intensively farmed landscapes on Earth. But by looking back, by understanding the gross, the coarse patterns that both shaped and the conditions to which an individual salmon or bank swallow or giant garter snake responds, that is something that is within our power. And so this idea of looking back, we can never go back. It's so important for all of us restorationists to remember. We can't just pick some arbitrary idea of what the world was like before and try to reproduce it in a snapshot, although it's something that we have tried to do and continue to try to do often. But if we can understand the processes which created and sustained that mosaic of different kinds of patterns and do our best to work with and approximate those processes, then we have a chance. Then we have a chance to give salmon and other native critters a world that they recognize. So the Sac Valley, before it was this mosaic of agricultural production, was a mosaic of wetlands. It really is a place defined by puddles, by water out on the landscape for long periods of time. This idea of dynamic permanence, that it wasn't the same place all the time. It looks very much like this rug, right? Maybe not so, but that you had a diversity of different interactions of water and landscape, allowing for different geologic deposition of soils, for a exuberance of different vegetative patterns that was shifting consistently. But it's defined by water interacting out on the landscape, often very shallow, right? That it's driven by geomorphology, by the interaction of geology and water with this, that created a couple really important fluvial processes that you can't understand our story unless you understand the valley. And the most important one is that most large river valleys we're accustomed to, right? The river is at the bottom of the valley. And that's true for the upper part of the Sacramento. But over millennia, as in actually quite a few other large river valleys, the river has laid down via carrying its own sediment out of the mountains, an elevated platform of its own creation. This idea of natural levees, which this arrow is pointing to, is absolutely critical to understand the wetlands of the Sacramento Valley. And you can't understand the salmon without understanding the wetlands, because the wetlands connected to the river. A wetland-river connected corridor, that's what this large river valley is, and that's what really all large river valleys were. So we're just showing here the site of many of the slides that we'll be looking at in a moment. This is the upper YOLO bypass. In the bottom right, you see Sacramento International Airport. This is the Sacramento River flowing up into the Feather River. This is the Sacramento here. And this is a LiDAR image. It simply shows the red are higher elevations, the green and yellow lower. And what you're looking at is that the high elevation is right along the rivers. And you have what are called flood basins as you move away. The lower lying shallow basins that would fill with water every winter and spring. Water flows downhill, right? It seems like that's beyond worth mentioning, except most times when I go into a conference room, people seem to think it flows down on a map. That what we're really trying to create are a gross approximation of the way that water interacted with landscape. And how it worked in the Sacramento Valley was spilling out over those natural levees into vast, shallow wetlands that could remain wet for months or even through most of a year. And these names that you see here might not be familiar for those that aren't familiar with the Sac Valley, but those are the names of our counties. But before they were counties, each one of those was a flood basin. Your name, the actual political jurisdictions of the Sac Valley are named for puddles, are named for wetlands, even though that is not understood generally in the halls of the legislature. So that all transformed. We went from a land of a mosaic of wetlands to one of a mosaic of agricultural production. And it happened rather rapidly. And I won't go into that in any great detail because the simple story is just that, it's simple. We call them dikes or levees or other ways of water infrastructure. What is it? It's a pile of dirt. We piled dirt along every single small creek, stream, large river, and we divorced the water from the landscape because it's inconvenient to have it spread out, right? And that divorce of landscape and water was done at a vast scale. We have 13,000 miles of levee in California. And it did allow the conversion to this incredible agricultural productivity that we have today. But it was done, this development, right? This sense of progress that's built into the language even, drain the swamp. What does that mean, right? Well, it simply is getting water off the landscape as quickly as possible. And I just think about all of human endeavor, whether it's the parking lot outside or your backyard, any agricultural field, a parking lot at the grocery store. Everything is moving water off the landscape quickly, and there are tremendous consequences of that alteration. So this idea that for 150 years, folks thought that the fish belong in the river and the river belongs in its banks has really shaped our imagination when it comes to what's possible in fisheries science, in restoration. How am I doing on time, Carson? Good. So what are those consequences? Well, the biggest one is pretty simple too. This is maybe a info-heavy slide, but all I want you to really focus on is, not that. In doing so, we have short-circuited the capacity of large river aquatic ecosystems. And I don't want to think about them as river ecosystems anymore, they're river valley ecosystems. That river valley no longer has access to what is really a vast solar panel. The floodplains in summer, look at this, are collecting all of that solar energy. And they're storing it in what? Leaves. That can be riparian vegetation. It can be the grass in a grassland. It can be, weeds at the edge of a farm field. It can be the agricultural crop itself and the residue left behind. But all of that vegetation is a battery. It's the energy that the river accesses by what? Flooding. So what is flooding? Flooding is the means by which a river valley ecosystem accesses the energy needed for abundance. The very energy that we have cut off from it through inadvertent diking and wetland drainage. So our story in the Sacramento Valley really starts with rice. When I was a kid, so there's 500,000 acres of rice grown within 100 miles of Sacramento. Rice is planted in the spring. It's flown onto fields by low-flying aircraft. And rice, of course, is grown, it's a water grass. It's grown in a puddle. And what would happen in fall after late summer harvest when I was a kid was that the farmers would burn those fields. And they burned them to get rid of the rice stubble so it didn't aggregate in, make big dirt clods that wouldn't allow them to make a nice smooth field surface for the next spring when they were going to fly that rice back on. Because if it's all lumpy, the rice settles into the depressions and you don't get an even stand. And if you don't get an even stand, can you guys not hear me?
Just for the recording.
Ah, for the recording, gotcha. If you don't have an even stand, then you don't get as much yield, and it made sense to burn the rice off. But what happened was you had horrible air quality conditions, and in the early 90s, there was an epidemic of asthma in school children, and they curtailed burning of rice. And the rice industry cried foul. Uncle Sam, the government's coming in, regulatory hammer, it's gonna be the end. And the second best way they figured out to deal with the rice stubble was flooding. Because if they reflooded their fields after harvest, you had microbial action that would break down the silica in that rice straw, and it would incorporate into the soil easily when it was plowed up the next spring. So you had a regulatory environment that had nothing to do with thinking about wetlands or birds. But for millennia prior to European development, the Sac Valley had been the heart of the Pacific Flyway. And the ducks, the geese, the shorebirds that had been migrating between the Arctic and their wintering grounds in California, Mexico, and even for some of the shorebirds as far away as the Amazon, suddenly knew exactly what to do with that, right? They settled down into these shallow, flooded fields and said, this is a wetland. And when I was a kid, ducks and geese, shorebirds were at all-time low numbers. They were about to be listed in the same way that we think of as our salmon stocks today. And over the last 30 years, we've had this tremendous resurgence of abundance on these fields, right? And this is the heart of the story, and we're about to get to fish. But the issue here is you can see them. We didn't get rid of ag in the Sac Valley. We didn't penalize the communities that were growing out there. What happened was the rice community saw that they could be part of the solution. And when they did so, they very, very rapidly started to adopt a series of practices that managed their fields, still in active agricultural production all summer, to be in fall and winter surrogate wetlands. And we had a whole guild of migratory birds that responded really quickly. And in this world where we just hear one story of doom and gloom and unraveling ecosystem after another, we had, in the midst of the valley, this explosion of natural productivity again. And from that came this idea, well, if farming and conservation can work together, and we have a co-evolved suite of native critters here, obviously puddles are important to puddle ducks, but could they be important to salmon as well? It seems like they would be. Time, Carson?
Yeah, 10, 15 minutes.
Excellent. So in 2011, this is part of my PhD dissertation, landing at UC Davis after a misspent youth chasing fish everywhere I could, and coming up with a couple ideas about how fish might use rivers, mostly up in the wilds of Alaska. I came back to UC Davis and stumbled into a amazing place where Carson Jeffres and Peter Moyle and Jeff Mount and Jay Lund were bringing together the disparate disciplines necessary to actually understand a river system. These rivers connect us, but they also flow through geology, geomorphology, agrology, ag economics, ecology, and the Center for Watershed Sciences was a place within the University of California at Davis where you could bring together all those disparate, siloed disciplines into a synergistic, exploratory way of looking at rivers and how rivers function and how we interact with them. And into this came this idea of, well, if a rice field can become a surrogate wetland for birds, what happens if you reintroduce salmon into a muddy puddle in the corner of an ag field? And for quite a while, floating that idea was just met with derision. You can understand. Here's a young kid. I'm starting my PhD, and I think you should give me a bunch of salmon so I can throw them in a mud puddle. And people weren't particularly open to the idea. But through some of our mentors that had standing within the community, Peter Moyle and Ted Summer among them, we were able to get a tank of 50,000 young Chinook from the state hatchery. And they showed up quite small, 45 millimeters or so. And we said, let's put them into a rice field. And Carson's going to elaborate on this story here in a minute. We did that on a rice ranch that's in the Yolo bypass, which is part of our flood control system, and that floods on a regular, if an infrequent basis, and that's a story that we can elaborate on as well. But the point here is that a large rice ranch collaborated with us and let us create an experimental floodplain for fish in the corner of one of their 200-acre rice fields. So after rice harvest in late summer, early fall, we went out and built a small berm around 5 acres and then constructed some pens, flooded that field using the agricultural infrastructure, the irrigation infrastructure. The truck showed up from the hatchery. We took these very small fish, and this was a real key point here, is that almost all of the research that had been done on young salmon at this point had been conducted on much larger fish that weren't a very good surrogate for the actual wild fish, but they were large enough to accept the tags at the time. And so we wanted to use fish that would have been similar to those that would be coming out of the gravels on the valley. And it was really a stroke of luck that right at that time, after we weighed and measured these fish. And Wayne is a key piece of the story that we'll talk about in a minute, and Carson will elaborate on. We had passive integrated transponder tags that had just got small enough to get into these fish. So a small subset of them were individually tagged, allowing us to track individual growth rates, which is key on getting the statistical power to really be confident on our results. And so most of those fish were released to be free swimming within that roughly 5-acre mud puddle. And then a subset were put into those pens so that we could recapture individual fish on a weekly basis, or I guess every 2 weeks, and measure growth. And so roughly 6 weeks after the fish had been introduced to that field, we drained the field and captured the fish as they left and looked at their growth. And it was truly spectacular. They went in small and came out looking like this. Oh, wait a minute, that was the wrong picture. Looked like this. These fish really are monsters. They're giant. They'd been doubling their weight every week. So the fish had gone in looking like every other hatchery fish, but had come out giving us an idea of what a Sacramento salmon should actually look like when exposed to conditions similar to those under which it is adapted, right? All of this is highly artificial. We're in a corner of a rice field. But what we're looking at is not we're not advocating for trucking fish into ag fields. What we're trying to do is do our best, given the constraints of the valley that we live in now, to understand how fish used it historically and how they might use it if we're able to change. And so these fish were measured and tagged, and we saw this incredible growth. And this was in the winter of 2011. And we started to ask questions about why they were growing like that and what the consequences of that growth might be. And I'll go through this rather quickly and then turn things over to Carson, who will really elaborate on the science of that story. But this is the underpinning of it. We started to say, and I'm a little embarrassed how long it took us to look from the fish to the food, but several years in, we started to say, hey, let's look at a cross-section of aquatic habitat within the valley. We have the river on one side, 30 yards over the river, over that levee is a canal. The canal is how water tends to move across the floodplain now in our agricultural dominant system. And on the other side of the canal are the fields. Those fields are where the shallow, wetland-like habitats now exist. And we went out and sampled each one of those. And in the Sacramento River under flood, we had actually quite a bit of food. There's 1,500 or so small invertebrate critters in this beaker. That beaker represents a cubic meter of water in the Sac Valley, again, under spate, in the conditions that are about as good as it possibly can be to be a young juvenile salmon leaving the system. In the canal just on the other side, there were 600% more bugs, and you can see the size. There wasn't just more bugs, but they were much larger, more nutritious bugs. But this is the story. Here, just feet away, just meters away, is a different environment, a shallow, wetland-like environment. And in that environment, there was 150 times more invertebrate biomass than in the river. So that's great, well, 150x. 15,000% more food available just on the other side. Why? Because water spreads and slows, right? This is the difference between fish of the same age, one which is allowed access to a wetland and one is not. The top fish, tens of millions of fish that look like that can come out of the Sacramento and the Feather River on an annual year, not even a good year. We don't see many of those fish again. That's because they're confined between levees in a food-starved system. One of our own creation, inadvertently so, but all we need to do is change the plumbing enough to have swim through wetlands, to have fish that in 3 weeks can look like this lower one. And that lower fish has packed its lunch, right? It is a fundamentally different set of odds that that fish survives and comes back as an adult than the top one. And that's because of this thing. You know, it's about time. It's about time that we acknowledge the role of time, of inundation, of residence time of waters, of interaction between water and landscape. In the Sac River, the water turns over every couple seconds. In the canal, every couple minutes. In the field, every couple days. But remember the wetlands I was talking to you about? The wetlands after which our counties are named, they would have stayed wet for weeks, months, or even much of the year. What we've done is short-circuited a very simple energy flow. Sunlight is caught by plants out on the terrestrial system, or if it floods, and I need to use my hands for this. A river, as we tend to manage it, is steep-sided, levied. You have relatively low amounts of surface area to collect sunlight, yet large volume of water. The moment that water spreads out on the landscape, you have a much larger photic zone, a much larger flood area, a solar panel to collect winter sunlight, right? So that winter sunlight is collected in floodwaters by phytoplankton and algae. That then is eaten by microbial and bacteria. There's a detrital food web there, as well as directly by zooplankton and other invertebrates. Those that is fish food. Small fish rapidly become big fish when given access to these dense, productive food webs. Doesn't take much time, but it does take time. And so what we've looked at is in about 3 weeks, you go from inundation, where there's very little food, it looks very much like the river, basically a food-starved environment, to one that is, we call it zoop soup. It's absolutely zooplankton soup. It is seething with protein. So in reducing our wetlands, what we've actually done is reduce the capacity for large river valleys to actually create aquatic abundance, right? It's that simple. And unless we're going to get connectivity back between our wetlands and our rivers, we are not going to be able to recover these fish. And we have a whole bunch of ways in which that might be done. Carson's going to speak to most of them, but I will just say that the answer is not to simply return large swaths of the landscape to wetlands. Where that's possible, and especially on the margins of farm fields that get wet first, that stay wet last, that are already marginal, those are great places to start to think about enhancing, about creating these kinds of on-farm wildlife and fish benefits, right? But for the most part, what we're talking about is understanding the sequences of biophysical condition that were here previously and mimicking them in working agricultural landscapes. And so what this slide is just showing the 1888 map where those darkened patches are the tules, the wetland, the emergent wetland vegetation. And that's fading back and forth to current LIDAR. And what you can see is like the 5 o'clock shadow on those deep peat soils. The wetland is still there. What changed on the floodplain was how we manage water on that wetland, on that floodplain. And so what we're trying to do is reestablish those patterns. Reactivating floodplain patterns on a landscape scale is what's going to allow us to get these floodplain fatties and to fundamentally change the cohort replacement rates of our stocks in the Sac Valley. And you don't really have to trust me about it. You can actually just ask the fish. This is what our colleague Eric Holmes put together on fish out on the Nags Ranch, right? This is how quickly these fish are growing out there. And Carson and Rachel have been doing research using different natural tagging mechanisms to track these fish throughout their entire, not just life cycle, but the population effects of being able to access habitat-like conditions that allow a fundamental change in body condition that then translate to full life history return rates. This is the simple idea, I suppose, is that the focus on getting adults into diverse watershed headwaters is where we get our resilience template. That's where we're going to create production of juveniles coming out of different hydrologies at different times in different spaces. But as those fish come down into the lower, more productive parts of our watersheds, that's where we get that capacity for abundance. So longitudinal access for adults, resilience. Lateral access into wetlands, that's the abundance. That's the ability for actual recovery. So if you wanted a 3-word recovery theory, at this point, I would give you swim through wetlands. Everything we're trying to do is to allow these fish to swim through wetlands. Carson, rather than do this, I'm going to hand it over to you. Please. Oh, I got to just say that. What am I going to say? You know, it's not rocket science, but it is physics, you guys, right? We're actually talking about energy flow. And if you don't have the energy, you can't ever expect to have recovery of these fish. This is really simple stuff in some ways. Hard to actually implement in some ways as well, but, you know, the multiple benefits of this work that we're talking about over vast landscapes, hundreds of thousands of acres, is being well acknowledged in the Sacramento Valley. When you spread in slow water, you not only create this incredible natural engine of productivity that I've been talking about for birds and for fish, but you're also spreading water so that it sinks back in and recharges aquifers. That's, in California, the fundamental bank account for the 4th largest economy on Earth, not just for ag, but for the water supply for our cities and for our economy. And so we have this, you know, you can call it a triple bottom line, you can call it common sense, you can call it cultivating ecological solutions on agricultural lands, you can call it nature-based solutions, you can call it so many things. But what it is simply understanding how a river worked, understanding how fish and other things used that river, and doing our best to approximate those patterns in our management. All right. Thanks, Carson. Where are you? Am I going the wrong way?
You're going the wrong way.
Puddle power.
All right. Do you want me on the handheld, or if we've given up at this point, I can just talk at the... All right. I'll try and stand somewhat still. Thank you, Jacob, and thank you all for being here. This is fun. Jacob and I have done a version of this in so many different ways and in so many different places, and it's so cool to be here doing it. And I'm quite grateful. I'm sorry you had to miss some of Jacob's slides, because it was funny. It's like, oh yeah, then he goes to this, and then he goes to this. We've done this enough times, so I would be sure you talk to Jacob about some of the other stuff that he's talking about. I will say that I come at this in a lot of the same places that Jacob did, but I come at it from the university side of things. I get to live in a weird space at the university. As some of you who are at the university know, is that we are oftentimes judged by how many papers we put out. But one of the challenges is that how do you make those articles be useful in what actually happens outside of the university? And how do we make our science usable to people who are not just within the academic circles, but people who are out actually working in the fields and who are making these systems function? And so I'm going to tell a little story that is, you'll see some of these. It's funny, I'm realizing that we do have some of the same slides. A little bit of history here and a little bit of context about how I got into this and how I met Jacob in this space and led us down this journey together, and how we try and use that science and quantifying the actions that we're making, because it's really important that if you want to quantify, or that if you want to make actions on the landscape, being able to come to the table and be like, we did this and this is what happened, is really important for as you continue to evolve those processes. but Jacob talked about this, so I'm going to kind of go through this a little quickly, is that historically the Central Valley was this large wetland, as Jacob described. We have changed it. And you saw that we've lost roughly 95% of our wetlands, and with it, roughly 95% of our productivity. It's had pretty serious impacts on the aquatic ecosystems. And to start that story of how I got involved in this and how we realized that we do have to think about this reconciled space, and that this place where it's not gonna look like it did historically anytime soon, but how can we find that place that works? And that story begins on the Cosumnes River. So the Cosumnes River is in the middle of the Central Valley of California. It flows out of the Sierra Nevada, and it has the unique distinction as being the only undammed river that flows out of the Sierra Nevada into the Central Valley, which is crazy to think about. You all have these most amazing rivers, and I remember when we came up last year, I was like, oh my God, you guys have nothing to worry about. This place is beautiful. This is amazing. Like, you haven't seen a truly destructed ecosystem until you've been to the Central Valley of California. And so the Cosumnes has this it's a unique place in our landscape because it doesn't have a dam. And when it rains, it floods, and when it floods, it moves across the landscape. And so in the late 1980s, there was a lot of work going on in the Central Valley. We have the Nature Conservancy, Canada is here, is that the Nature Conservancy in California was actually in the 80s trying to figure out how to replant riparian vegetation, our valley oaks, our cottonwoods, our willow species, and they were greatly struggling. They had lots of plantings, it wasn't really working. And then you'll see this circle or this square or polygon that I have here, this green spot. That was a levee breach in 1983. And this was a tomato field, but there was so much sediment that came out in 1983 that the farmer took that 5 acres out of production because there was about 1 meter of sediment that came out there. And they realized that they weren't going to be able to farm that, so they just took it out of production. And then here we are 10 years later, and a forest started to grow. And this was the realization that we had lost a lot of this process in the system. And so the Nature Conservancy, our state and local governments, and some of our federal agencies, and Ducks Unlimited is here. I saw also we have some DU folks, is that DU was a big part of this, is that they realized that maybe we have this opportunity to start reconnecting the floodplain and seeing what happens. We're spending a ton of money and effort to try and rebuild riparian and floodplain habitats without the actual processes that make them work. So in 1997, this is 2003, it's not 200 and then a 3. This is 2003. So in 1997, we breached levees on the Cosumnes. You'll see that these are the same fields. We kept lots of it in agriculture. We moved it over to ag. And then we started to see what happened. And we saw immediate response for this. We started to see on the bottom here, you can see that there's what we got? You can see that there's a sand splay here, and another forest is starting to come up. We breached here. We excavated this pond. There's a forest coming up here, there's a forest coming up here, there's a forest coming up here. And all of a sudden, with just that little bit of reconnection, we weren't planting these trees. These were trees that we were recruiting naturally. And then in 2024, this is what it looks like, which is wild to see when you actually start here in 1993, and 30 years later, you have a whole riparian forest. We still have a lot of agricultural lands in this system, and it's primarily rice farming. But we were able to see that change in the landscape, and we really saw a change in the aquatic ecosystem as well. And this is work that was done in the early 2000s, where we got to see that it was funny that at this time we didn't understand what the floodplain was doing. It's funny, it seems so common now that we have these conversations, but in the early 2000s, when we spread that water out, we realized that, holy moly, there's a lot of primary and secondary productivity out here. What is the time frame to doing that? And then what happens? And so up here you see that this is the primary production. You see that it's really heterogeneous, but we see this just like booming of aquatic productivity that's happening out there. We see invertebrate densities that are amazing. And then we saw, this was our first insight into what happens when the fish get out there. This is actually my master's work. And these fish were the same size 5 weeks earlier. And one of the fish on the left were reared in the river, and the fish on the right were reared on the floodplain. And it was a pretty big thing. I've actually made a career out of this photo, by the way. This is, if I were, when I move on, this is going to be like, oh yeah, Carson made a career out of this photo, in that it tells a story with just the image. And I remember that when I published this paper, I had to fight so hard to get this image in, because the reviewer said, but you have that same data in a graph. And we fought and fought, and it's funny that this image like comes back to me. People present this photo to me in presentations. I'm like, oh no, that's actually mine. It's wonderful. I was giving a lecture at another university in our area I guess it was last month, and I gave this picture, and one of the students in the class said, oh, my grandma has that printed out on her door at work. And I was like, I love your grandma. This is amazing. And so, but it tells a story of what is realized when you restore that process. And restoring the process, this is when I met Jacob. And I was excited. I was like, oh, we're gonna go down, we're gonna take out levees, we're gonna change the world. And Jacob pointed out that scale is real important. And he's right. And that when we want to start doing landscape scale actions, it is important. And I think that I was looking at this roughly 50-acre area on the left here, and I was like, well, what can we do? And you look at the picture on the right, which is the Central Valley, and I'm not sure you can see that blue dot right there. That's actually bigger than our floodplain. And you can't see it on the landscape. And so to have meaningful action when we started thinking about this is, there you go, I circled it, is starting to think about what were our opportunities to have meaningful change. And it can't be at a postage stamp in the Central Valley. If we want to actually see large-scale recoveries of the fishes, then we needed to start thinking about this in a different way. And that's when I met Jacob. Well, actually, I met Jacob right a little before, but that's when Jacob really got to me and started saying, you need to think about this differently. And so Jacob talked a little about the Yolo bypass and where we're at in here. This is the Yolo bypass in this bottom part. This is the Sutter bypass right here. This is the main flood control that saves the city of Sacramento almost every year. Without these flood control systems, the city of Sacramento would not exist in its current form. It would be inundated quite frequently because we can't contain that river in the levees. And when you look at this from scale, I just showed you those pictures of that beautiful place where we saw the recovery of the riparian areas and the fishes, is that when you start looking at what actually gets inundated and the scale, it changes when you go into these opportunities. And even though it's just a small bit of what it was, we started thinking about where can we do this, and where do we have historic opportunities? And Jacob just went over a lot of this, but realizing that all the juvenile salmon that were moving out of the rivers during the winter and spring months, they had spent their time rearing in the rivers. They were born there, our winter freshets, and they were coming down. And this provided it's part of the life history of these fish. There's fish that stay in the rivers. There's fish that move out early. We see this diversity of life history strategies that we have more or less cut off. We don't allow fish in the high elevation areas anymore. We're working on that. We also don't allow those small fish that are moving out access to these habitats. And we've ended up in a place that is very small in providing resources to them. And with that in mind, Jacob's like, we have to go to the bypasses. This is the place where we have flood protection, we have farming, we have the birds are using them, and we need to be part of that conversation. And so we started down this path of trying to understand how water moves across into those places, what fishes have opportunities, and what are the things that we can do differently to think about how they use them and how can we quantify the benefits over time. And this is a decade of our hydrology. We're seeing wet years. Yep, 5 minutes. Oh, yeah. Yeah.
There's a piece that.
Yeah. And I also, if you guys need to stop, I'm also.
There's a piece for context here for people from British Columbia that I had to go to Sacramento to understand this. When Carson and Jacob talk about the bypass, you have to understand what this is. Like when they're showing these pictures, the Sacramento River, when I drove into Sacramento, I said, yeah, I was looking for the bypass. I didn't see it, but I went over this bridge that took me 5 minutes to go across. And Carson's like, yeah, that's the bypass. And then you go over the Sacramento River and it takes you 20 seconds to go across it. And it's like, yeah, that's the Sacramento River. And so this bypass is a massive floodplain that is occupied with farms mostly, but some other infrastructure, farms and roads. And that's what they're talking about. This is designed to flood. It is occupied by agriculture. It's flood-compatible agriculture. And the river's confined inside the levees. So all year the river runs in the levees, but at flood time, the way they manage their water, the flood water is directed through this bypass, and the bypass is massive. It's not just, I was imagining the other way around, the river's big and the bypass is small. It's not. It's complete opposite. So I'm just interrupting this wonderful story so that people from British Columbia could start to wrap their heads around this, because understanding that is how you then think about, well, what are our potential opportunities to apply this thinking, but in a different context here. So sorry for that interruption, but I think it's good to share that with the people here.
No.
Thanks.
Yeah. And if there's anything else, I can also be interrupted, like Jacob said. I'm totally comfortable in that space. Yeah, I want to make one quick point here, and then I'll get there. As Jason said, these are big areas. So these two bypasses are about 85,000 acres together. And so I will show actually what it looks like through the hydrology, is that we have this variable hydrology every year. And we've seen wet years, we've seen dry years, and this is what the river hydrology looks like. But it's not what the floodplains look like. We still have these thresholds before which we get floodplain inundation. This is the frequency over this decade that the Sutter bypass, the smaller of the two bypasses, gets wet. Is that we only see it in about 6 or 7 of the years. We see a couple blips. It's actually not a lot of time. And when we look at the big floodplain in the red here, you see that it's even less time. And so one of the things that we were trying to figure out is, well, what does that actually mean for the area of inundation? And you can see here on the left now is we have the map of the bypasses on the top, and we have the stage of water on the bottom, and you can see the proportion of area that gets inundated. So what happens is, as the water comes up, is you can start to see water just barely blinking on the landscape. And as it gets higher, is we start to see area that becomes, well, it's funny how that moves in different places. It actually used to go along with the dots. It doesn't anymore. Is that we actually saw, like, what does meaningful floodplain inundation look like when we're talking about the frequency within which these fish have opportunities. And this is at the red part. When we start seeing the red on the graph in the middle, this is what it looks like, is we start to see tens of thousands of acres that are inundated at that point. And it becomes a landscape scale change where we see fish that are out there. And then we're off the charts apparently by the dot there, is that we see landscape fully inundated with water. And fish are, what is my time, by the way? What time do you want me done? 10:35, so 3 minutes? Holy moly. I blame Jacob. So I'll be quick. So the point is here is that we have these different opportunities of how the flood works across the landscape. We have these small-scale flood events that you see here on the bottom, and we have these big, large-scale flood events that are truly impressive. And the ecosystem benefits that come out of there are important, but it's also the flood protection that is arguably more important at this space. That's what allows us to have this opportunity, is that there's the flood protection side of it. I'm going to blow through this because Jacob already talked about it, is that we see these kind of ecosystem responses. But I want to get to this part, and I'll be quick about this, is that we have to justify our changes to the landscape in a way that when we just spent a big chunk of money redoing our flood control infrastructure so that we could have salmon accessing the floodplains. And when you make those large infrastructure changes, so we said, well, how do we know we're doing anything that's meaningful? And working with small salmon is really hard. How do you know a 65 mil fish benefited from that habitat into either the ocean fishery or the fish that come back as adults? They're too small to meaningfully tag. It's very difficult to capture and monitor these juvenile fish as they're moving through. And so Rachel Johnson, who is here, Our lab has worked on building up these natural markers inside of the fish that we can understand how fish use different parts of the landscape, and when they come back, where those fish spent their time, and do we see disproportionate uses of habitats? Hold on, Emily, I gotta go. And so the idea is that if we are able to track fish from a very small size to adulthood on different parts of the landscape where we're making different management actions, then we can understand the benefits or not of the actions we're making. And so we had a student, Miranda Tilcock, who, for her master's work, developed this idea that there's an ice escape, that for the eye lenses of the fish, actually I'll get to the eye lenses, we haven't even got there yet, I'm all flustered now, yeah, okay, I'll hustle, but, yeah, yeah, I'll go. And so, yeah, Jacob's easy, yeah. Is that we notice that there's this difference in sulfur in particular on the landscape, is that there's different isotopic values of sulfur that are in the landscape. We've realized that one thing in particular is that it's very different between the floodplain and the river. And the beauty of sulfur is that it's a great marker for what the basal food web sources are, and that it gets incorporated into the fish. We have their eye lenses and their muscles, is that you are what you eat, whether you like it or not. You know, it looks like a bunch of us are made of coffee and pastries this morning. We're gonna look like pastries and coffee isotopically. And in the same way a fish is as well, is that it incorporates those isotopes into their tissues. And we realized that there's a unique tissue in a fish. There's lots of fun tissues in a fish. But for this question, the lens of the eye of a fish is a great diet history. It's a great diet journal. And it keeps track over time of where a fish is spending its time if it's feeding in different food webs. And what you can see here is that we got really lucky, is that we have these two amino acids, cysteine and methionine, that have a lot of sulfur in them. And so we're able to look at the very small inner layers of a fish's eye lens and know which habitats it was using at that point in its life. And so we have this conceptual model that, okay, if we know that there's different values, we could go through those eye lenses and reconstruct these histories. So what we do is, Rachel and I have a whole group of undergraduates and early career researchers that peel eye lenses for their job. And so just, we think about that. It sounds crazy, but we've realized the importance of this. And we pair that with, I'm not even gonna get into the otolith work. I'm gonna bypass that, but we also pair otoliths where we're able to look at the rivers from which those fish are from and know which rivers they have opportunities to use. So if we sample fish as they're leaving the freshwater environment, we can say, hey salmon, you are from this river, you utilize these habitats during your outmigration in those rivers, and we change that, then we say, oh, we're seeing the proportions change over time. Then we end up with some graphs that look kind of like this, except for the blue is gone. You can see it. You can see it? Barely. So the idea is that when we start looking at floodplain usage versus non-floodplain usage at different points during the outmigration, so you can imagine the Fraser, if you have tributaries and the main stem monitoring, then we're looking at fish leaving the different tributaries, looking at how they're using different habitats within those tributaries, and then at the bottom, we sample them as they're leaving the freshwater environment. And we can say, okay, this fish is from the American River, this fish is from the Sacramento River, this fish is from the Feather Yuba, whatever it is. And what are the proportions of those fish that are utilizing floodplain habitats? We can start to understand, is there this benefit that is translated from that juvenile rearing phase into the fish that come back as adults? Because those are the fish that we ultimately account in our population estimates. Those are the fish that ultimately dictate the management actions that are happening on the landscape. And what you can see here, for example, is that the American River has very few off-channel fish at this area. The Sacramento River has very few off-channel fish up high. But by the time they move through this flood system, as you can see, we're about 60% of the fish that are making it down to the bottom are using off-channel habitats. And we're starting to understand what are the proportions of those fish that are moving through that are using those habitats. And that comes into these really important questions of, as we alter the landscape, are we seeing that benefit translated to adulthood? And you can see this is one cohort of fish, or these are actually two cohorts of fish that left in 2016 and 2017 and then returned 3 years later. So these are the same cohorts of fish. These are the juveniles as they left the freshwater environment in those years. And then these are the adult survivors where we collected their eye lenses and otoliths after they spawned and died on the carcass survey. So we have a group that's going out and collecting eyes and ears out of fish. So also think about how good your jobs are right now and be grateful you're not collecting eyes and otoliths out of dead fish on the side of the river or having to do them in the lab. And so what we see here, though, is that for this group of fish, about 15 to 20% of the juveniles use floodplains, but almost 50% of the fish that came back did. And for this other cohort, what you'll see here is in 2017 was a wet year. We saw about 25% of the juveniles use floodplains, but 75% use floodplains are the fish that came back. And so that the benefit is being translated from the juvenile to the adult return. And so as we start modifying the landscape, we can understand those benefits, because it's really important to be able to quantify when we're spending resources to change our management actions, restore habitat, reconnect habitat. If you don't have a way to count it, because when fish come back, you don't know where they spent their time. And it's one of the things that we spend a lot of our effort doing, is being able to quantify that, because that's ultimately really important, that as you look across this mosaic of habitats on a landscape, is it this one that's important, or is it this one that's important, or is it this one? And which one should you spend your resources? And so we really work hard on trying to do that. And so when I think about what we have in our future and where we were in our past, and I think that in California, we're kind of reconciling. I think in a lot of ways, even the beginning of the meeting today, when Jason recognized the First Nations communities that were here and who are part of this now, is working with the Winnemem Wintu right now, is they have not been part of the conversation in the past. And I think that you guys would probably say yes. I see Chief Sish nodding her head. And it's something that we can't have going forward, is that lack of voice at the table. And I know that for other projects that we're doing, not just the floodplain stuff, but all of our work, is having that voice at the table is very valuable. It changes the way that we think. And Chief Sish talked about earlier is that talking about the traditional ecological knowledge and Western science. And it's that blending that I think that we have been informed in how we differently think about the work that we do and incorporate that into our space is really important, and changing the way that we think from our Western science and how we value and how we quantify things has changed. And I think that that's really important. So as we're going forward, that's really different in how we think about it. And I also think that one of the things that Jacob, he flew over in his spot, is the number of partners who are part of this, is bringing together the indigenous communities, the farmers, the NGOs, the academics, has made us have a space where we are much stronger together. And when we first started this, Jacob and I gave tours twice. Every Wednesday we gave a floodplain tour, and just bringing anybody who wanted to hear that story along on the journey. But I think that the thing that really I get excited about is that we also really work on the science so that we can justify the actions we're making and the effort that we're putting into this. Because without a good standing, it's hard to convince people to spend their resources. And it's all of us together that build that science. And Chief, I know you said it's science. I'd say we're Western science, but I think it's the science that we do together. And Maureen, you are our what is it? What did you call yourself as your title again? You're the lead traditional scientist. And I think that it's the traditional scientists and the Western scientists, and I wish we had a space that we could be in the middle, that I don't know how we could call ourselves together, but I think that it's that together space that gives us a bigger voice to move it forward. So, bringing in all of our graphs and all of our things, but with the context of what that means at the bigger picture. So I think with that, I'll wrap it up. And this is Jacob and I when we were younger. But I think that's what we got. What are you doing? You want to go?
I was
more?
going to just go back to this here, right? Oh, keep talking.
That's all I got.
No, really?
Yeah, I mean, I could go more, but I think
All I did blow, through. It was so important coming to a new place where I spent maybe more time trying to explain the landscape of the Sacramento than I should have, because it didn't allow Carson to really move into his, or into his talk and into the depth of the science, which is amazing, or to what we're doing about it. And I know that's really why we're here, is what we're doing about it. And so before we turn it over, I'd just say that what you're looking at, that all of those logos on the page, is simply that this story has seeped in to the Sacramento Valley. And the story is that the science makes it really clear that endangered fish are not a necessary outcome of development. They're a direct result of the way in which we developed, of the interruption of the natural processes that create and sustain a world that fish can actually recognize. And that together, agricultural producers, the water suppliers that are some of the most powerful entities in California politics, the conservation agencies that is from the Nature Conservancy to Ducks Unlimited to California Trout, to all of the different folks that often have bickered amongst themselves, have put those aside to say we need to work together. So when you bring that and the local, state, and federal governments all together, and we've been able to do that as well in getting an MOU signed by all of the federal agencies and state agencies that say, we're not doing enough. Yes, what we've been doing is really important, but we've been staving off extinction, and we need to move into something else, into true recovery. And the birds have shown us a way forward that we can translate into fish. And when we do that, it's not just the right thing to do. It's not just justice beyond specific communities, but for the larger community on the landscape. But it's also the most profitable way forward. And that's something that I just wanted to leave you all with moving forward, is that this coalition understands that when we come together to create a functioning river valley, what we're actually doing is creating not just a sustainable, but a profitable economic model that aligns ecological and economic outcomes in a way that makes sense to an individual farmer and to the governor of the state. And that's fundamentally different, and it's based on not science, but the co-mingling, the synergistic co-storytelling that Carson was just talking about, and that Chief Sisk and Michael and Maureen are really courageously and beautifully undertaking now. So thank you for having us, and sorry we botched our presentation.